For today's conversation, I have things to share, especially with the Super Mario reinforcement. Let me first show you the code that I'm currently running. So this is the code currently I am now running, and it now takes more than now 2 hours, and currently still is under the activation. And let me just share how it works. After I run the code around the 30 minutes, so that if I just play, then you see, so the Super Mario is now running. So it seems okay, but actually it is not. So this is my current best. So that my Mario does not know how to jump this height. The part of the reason for this, like the lack of the nice performance, is about the computing power. So I just put less than 30 minutes to just learn. I mean, the compute the repeat the algorithm less than like the 30 minutes, so that I just try to just extend the time as much as possible and try to see whether or not the performance is really improved. And I need to eventually just move to the Google Colab, for example, to in order to use the GPU and CUDA. But anyhow, so that's currently what I am doing. And so the code is not hard to activate by ourselves. So let me share how to do it. So one can simply just type on the Google website, Super Mario OpenAI. Then one can just jump into this official website. And all want to do is just install the necessary packages for sure, and then just copy and paste this part. Copy and paste this part. And once you just copy this part, then Super Mario just pop up and he just run play as human. Simply that's it. So what I today wanna share is the sort of the mathematical understanding behind this code, including the computer science part. I mean, the machine learning, like the algorithm that is the so-called convolution neural network, and the deep Q learning, or DQN briefly, and the behind mathematical like the reason, because we are mathematicians, we want to know why the algorithm really just works well. So that's today I wanna talk about basically. If we go further on let me just show you this part. So I prepare the note for our conversation today. Let me first share the link to you here. And let me try to explain first. Because I'm running the YouTube, time to time I have a conversation with the engineers, and it's pretty difficult to really explain the mathematical part. And this is like a typical the content that is hard for me to make make the reasonable conversation with them basically. But for us, we are all familiar with the basic like the analysis and topology, linear algebra. So it's just basically that's about it. So the code, if I show you first. So first, just import the necessary libraries basically and the packages in order to just proceed the learning and the performance. So that in the Python, like the algorithm, there's a so-called Mario class. And the Mario class is run based on so-called the DQN. So DQN is just a brief word for deep Q network. So this Q just means the quality. So that the Mario class is run by this like the DQN, and there's also the class of the DQN, and the class of the DQN is work, of course, based on the certain like the TensorFlow, like the library from the certain like the Python like the package, but we can just simply just import once we just get used to like Python language. So it basically uses so-called the convolution neural network, as I said. So in this like the DQN class, it uses 3 times of the convolution neural network. And once one just use this one, then just use so-called batch normalization and just use the activation function. And in this case, just use the so-called ReLU function. And simply that's it. And this DQN class is defined by simply using the CNN here, and this DQN is applying to get the policy and the target that I will try to explain via my note. So the Mario class, in summary, is run based on the DQN. That is just nothing but applying the CNN, and the DQN class is used to update the two parts. One is a policy, the other is the target. So once the Mario class is defined, then eventually the output, if I just go further and further. So this is the part so that the Mario like the game is running, and this action is taking the new model here, and this new model is taking the Mario class. Simply that's it. So in summary, so once this code is using this command, then the Mario game is in under the activation, and this one is based on this line, and this line the action is taking the model, and this model is updated based on the Mario class, and the Mario class is taking the DQN class, and the DQN class is working based on the just a CNN. Simply that's it. So the structure is that the CNN is used to define the DQN, and DQN is just is used for the Mario class, and the Mario class is to update to policy and the target, and that's for the update for the like the performance of the game. Simply that's it. So if I now go back to the note.
Yeah, I want to
Yep.
ask a question about the
Sure.
code. So
Mhm.
CNN is the part where you do the machine learning. Is that the
Right.
case?
Yep.
Okay.
So there is a part for the learning. Let me show you. Uh, should be here. So there's like the cases. Either one uses CUDA. So in the case of using the GPU, and otherwise one use the not CUDA. Uh, so this is the part. This is the part with the iteration that this learning is based on the Mario class. And once one use the Mario class in this iteration, then the CNN should be under the activation.
Inside of the Mario class, you're doing the learning, and what kind of information are you taking in as the training data?
Yeah, that's a very good question for sure. So let me try to compare with the first this one. So there are basically two components of this game. One is so-called the action, the other is so-called the state. So if we naively imagine how the Mario game works, then we usually use just the keypad.
Mhm.
And the keypad affects the game to just affects the performance of the Mario. Simply that's it. And in the case of the reinforcement learning of this game, so the state just represent just a picture, each pixel. So the state just represent the current like the or like the possible like the pixels, and the action is based on those like the state to decide which action is the best possible action based on the certain model to determine affects the like the just the keypad like the action. So the action just means just either go right or left, jump, simply just that's it. And the current state just takes just a whole bunch of the like the pixels, and those pixels are updated based on the CNN. So if I go back to the code.
And I think there are two types of state. One is like the tube where you can interact with. It's going to block you, right? And then the other is like the background state. They're not interacting with you.
Of course, we can interpret intuitively in that manner, but the reinforcement learning, in my understanding, is a bit different in the following sense. So if I just go back to the official website here, and what you can see is that, so this is just a very just a simple, but there is the version of the Super Mario then we can import. So, and now I'm currently using the version V0 to just use the just a usual like the screen. So the pixel reflect all possible colors of the just a usual like a Mario game, but one can also use the other versions, for example, such as like a such a color, So each version represents a different state in a sense that the pixels reflect a slightly different data, right? You can now see it. So there's a part, I think I can show you this part. So that once I import the Mario game, I need to decide which version I need to import. And once I import that like the data, then each like the pixel data, even though we are running the same Super Mario game, but each reflects the different like the data basically. And the model should be run based on those data. And so that there are essentially two pieces in the class of the Mario. One is the target based on the state and the action, so that it takes both the current action and the current state. That means that's a collection of the pixels. And it also evaluate the policy, but I will try to explain those mathematically. So that it's just nothing but just taking just two pieces. One is the policy, the other is a target. And the outcome is also the new target with the new policy. Simply that's it. So the way to think is the following. So so there's no reference. So about this is my real understand what was really going on. And I think so for mathematicians, it's very easy to make the conversation what is behind. So we are all very familiar with either the fixed point theorem or the contraction mapping theorem. So I don't think I need to explain that proof for any of you. So given the complete metric space, right? Then we can start from the continuous map, and we require this condition with the weight gamma. Gamma should be strictly less than 1. Then under this contraction condition, we know that there's a unique fixed point. Is that okay for all of you? We include the intuition. It's very clear, right? So let me just skip the proof. So yeah, but it's sometimes very difficult for explaining these types of things to the engineers. What is the definition of complete metric space? But for us, it's fine, totally fine. So we will just apply this one so that so that we need two objects. One is the I just called by the value function, and the other is the policy. So the value function is the function that takes the element of the state. So the state represent different in the concrete like the machine learning situations. For in the case of the Super Mario game, so the state just represent like the collection of pixels. But in the different like the situation, like the learning, like the music and all different situations, the state space might represent something totally different, but it's okay. But so there's just an abstract notion of the set we call the state space, and it takes just a real value. And the thing is, we will just collect all possible like the value functions. And the way to put the mathematical structure is that we can regard it as a complete metric space with the subnode. Is it clear? So that if necessary, we will just assume, for example, this S is just compact, but in the like the research like the papers, such an assumption would be really matters as we mathematically like have the concern about it. But we just use this as such a like subnorm to just give the equip with the complete metric space structure on the collection of the value functions first. And the policy, so this is also the common name, that this is a function that takes the collection of the actions with the collection of the states. And it usually so maps to 0 and 1, and this has certain like the variation. But the reason I feel this is standard is that usually the policy function is defined in terms of for the machine learning papers, as far as I just read, is defined in terms of Markov chain or certain probability like the value. So that's why in terms of the description from the probability distributions of problem mass functions, it usually takes from 0 to 1. But there might be certain variation, and so that you can just assume this is real value if you feel that might be more general. But the policy is just nothing but the function, and there might be the necessary like the condition on the function depending on the context and the applications, but essentially it's just nothing function from here to here. And also we can put the complete metric space by just using the subnode. Is it clear? So that the reason to require this structure is to apply the contraction mapping. That's the reason. So that we just need to see if we simply just apply this theorem, then we just need to construct a continuous function with certain this gamma with the contraction property. And we just need to see, then we can simply apply this theorem, and we just need to see how to use this fixed point, because theoretically the unique like the fixed point is guaranteed. So the way to use is so-called the Bellman operator. And this is the part that I want you to appreciate when you read the code with the, like the similar situation. So if I just go back to the code, for example, so say blah, 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 blah. So that there should be the part for the, let me show you, such as like the mathematical formulas, for example, and there is some like the weight that is gamma that should be strictly less than one, and there's certain like the formulas, and if one just search from Google like the DeepQ learning, for example, and let me simply just quote the DeepQ first. This Q represent the quality of the, I don't know what color represent the like the either the like the performance or the certain model. I don't know, but it might just represent the cost function. So in the Wikipedia page, it uses the code name to the reader, but in my like understanding, it usually just uses from 0 to 1, but doesn't matter at all. So there's just a complicated expression of the updating the new quality function here by using this expression, then, and what I want to claim is this complicated expression is just a nothing but the applying the expression of the t function. So let me just now go back to my note. So now if you just see these types of the expression of the function, so let me try to be rigorous mathematically. So the reward function matters depending on the context, so that the reward should be defined individually depending on the each like the application and the context. So that let's just fix this as just simply just a function that takes the state and it just evaluate as a value depending on the like the context. But this can be changed a lot. And also we fix the policy function. Then with fixing the reward and the policy, then we can define such a function that takes this expression. The reason to take this expression is the following. So that what one can argue is that this map becomes a contraction mapping, because if we take the subtraction before taking the subnorm, then in fact the reward doesn't matter. We can simply just cancel for the reward. And if we just look at this expression, so that we already multiply by the gamma, which is strictly less than 1, so that this gamma should be taken out. And this expression should be controlled very nicely in terms of the subnorm.
Why is the reward just cancel?
Because if we just take so if we use the different two functions from V to V, we will put the same elements with the two different functions. Okay.
What
So
is
that,
different? Put the same element.
so so this v should be taken over here, So this v, let me try to say it, is taken this v in my notation is the collection of the value functions. So with choosing two different value functions, so we will still take the same like the element from the state space. So that if we take the subtraction between them with the different like the v and u, still those s are the same, so that we can take the cancel.
Uh-huh. Uh, the when you run the contraction, I'm imagining you're taking two different things within a metric space. And how are they different here?
So in the definition, so that we need to check this condition. We need to check this condition, right?
Yeah, so you have X and Y. So
Yeah,
what
x
is
and y. So this x is now taken as a set v here. So this set v is the collection of the value functions, so that we will choose two different value functions. And then we will evaluate with the t that we construct. And we need to check this condition in terms of the subnorm.
Uh-huh.
Okay, so that if I just go back, so we take so this v is the collection of the value functions, and we choose two different functions, so that let us denote it by v and u. Then we need to check it. So I will represent this phi sub pi as a target t. So I want to compare the first line with the last line. So this is the outcome I'd like to get. And in this construction of the map, so the S will not be dependent. I mean, this part is nothing to do with the V. So that's why.
Can you go back to the definition of the function? Because this part I really don't
Sure,
see
sure.
how the reward depends on S, and then other things depends on other things.
Okay, so we first fix the reward function. So this codomain is not a big deal, so that you can change the codomain as depend on situations. But the domain should be the state space. So it takes a state. So we fix the reward and we fix the policy first, and based on it,
So
so
reward
depending
only
on our
depends on state. It does not depend on action.
so the reward does not depends on the action,
Okay.
but it also depends on the like the context as well. So if I show you, but when I read the so it matters depend on the situation, but in this situation, for example, so you can see that the action is not taken inside of the river, but it might be different. So this is just a part of the construction. So one can also define the river depend on situation, but one just need to match the purpose. Simply that's it. And it might just simplify situation, and there's a lot of such a like the situation. The river does not take the action. Simply that's it.
How do you see that the reward here actually takes the state? It here, I just see it does not have any variable that it's taking.
I um so the reward so the main reference I took is from the ARPAGO algorithm, and the ARPAGO algorithm exactly reflects the setting I represent here. And
Hmm.
the reward just means that for the each state, so it just gives her like the value. So in the case of the ARPAGO, for example, either it defeats the other like the player, or it should be lose, or is still inconclusive, for example. So that the state in the case of the Go play, so depending on the current state just represent the like the current like the situation of the Go play, so that the viewer just evaluate the current like the situation, for example. But so one can just make the mathematical modeling for the viewer function in this case. So that if you just point it out, so why this is makes sense. So this is not the mathematical part. So I just use this modeling. Simply that's it.
Hmm.
So if we just assume the function, I mean the domain of this function is just S, then I can just use this one. But if it takes the action as well, then one can also twist the definition slightly. But the purpose is to just make the contraction mapping. That is necessary condition, in my understanding.
Okay, so now we're looking at phi pi, and it goes from V to V. And V, uh, should I should I think of V? What is V again?
Yeah. So there's just two things we are using. One is the value function.
Value of functions.
So value just evaluates the like the current situation. So in the code, you can just assume the value represent in the Mario like the code as just a, for example, like I bet one can just regard it as just a target, so that it just evaluate the like the current situation, so that there are just two different types of the function. One is a policy, the other is a target, whatever the terminology is. So I think we can just use any term. I think each of them are quite standard. Yeah, but anyhow, so I just use the value functions from the ARPAGO reference.
So value functions. Here you have S tilde. Should I just think of it as S?
Let me see. Yes, this S and S tilde should be regarded as same. Yeah, sorry for the bad like the notation.
Okay, so this is the collection of all the function from the space that contains all the state to real numbers.
Yep.
And now we're talking about phi pi and u and another function which is v, um, and they act on phi pi act on U. How does phi pi act on U again?
So we wanna define from the value function to itself
Hmm.
so that the inputs are just three tuples. So the R, pi, and V. So R and pi are already given
Hmm.
so that we can now associate each V to define such a like the expression. So this gamma is also given, by the way. Gamma is just some number between 0 and strictly less than 1. So the reward is given. So this part, there's nothing to worry about. And this V is now taken over here.
I see.
And the policy, I just define the policy in terms of the certain probability distribution. So I just use this description here. So this is already also prescribed.
I see. Which is why the U only show up at the end of this expression.
Yeah, so the outcome also becomes the function from S to R as well.
I see.
And I think this is very important in the like the reinforcement learning. This is usually called by the Bellman operator, but there's a like the twisted version of it. But essentially, this is the necessary like the essential description as far as I understand. And I'd like to keep this expression because this expression has a certain benefit that I'd like to explain. And
Hmm.
also, this is at least one important class of the Bellman operator, but there's could be some like the variation from this description, but it's not actually a big deal in my understanding. So it is not difficult to now check. It is contraction mapping. So now it takes two like the inputs, right, from this set. So that let's just take V and U. Then this real is nothing to do with this like the V and U, so that we can just cancel. We can just cancel. Then we can take this gamma out. Then the rest of the expression should be written nicely in terms of the soup distance. That's the way to drive. Is it okay with you? So then by just using the necessary property of the construction, then one should just argue that it should be just bounded by the soup distance so that so this is just a way to just construct the necessary like the mapping. And the contraction mapping is necessary because we'd like to eventually use the fixed point for our application. And by all means, as long as we can make it to be the contraction mapping, there should be the possible like the variation of such an expression. Simply that's it.
And the part about probability distribution sums up to be less than or equal to 1. Is it because they're probabilities? So,
There are probability, and people usually use a so-called the base rule or whatsoever, but just use this like the product and summation becomes the meaning of the probability, and then one should be able to just control. And yeah, here I use the like the implication of probability distribution in this R expression to just make it to be bounded by one. But just the goal is to just make it to be happen. Simply, that's the part I want to just share.
awesome.
So then we can now apply the contraction mapping theorem to get this element, which is a unique element, depending on this V. Is it okay?
Oh, yeah.
So from here to here, then we fulfill the necessary like the requirement for this theorem,
Hmm.
so that there is a unique element that gives the fixed point.
Mhm.
So what I want to remark is that there could be possible like the variation of such an expression as long as we can fulfill this condition. So this is just a goal. And we just need to see why we want to get this fixed point. The reason is the following. So the necessary components are two functions. One is either the policy, and another one is the value. And what I show you is we should be able to construct from one value function to the another value function by using the fixed point theorem, right? That's possible. So that now what you can see is the following. So yeah, this is the key, like the scheme, why one need to consider the fixed point. So now what we can see is that now let's just assume the reward is already prescribed, reward, gamma, all those. So let's just assume this pair is already given, R and gamma. And let's just construct this map by using this construction. in this node, okay? So let's just fix this construction here. Then what we can see is that for each pi that associate to this map that we construct. So as long as we have pi, that gives this map. So we start from the policy function that gives this continuous function. Then what we know is that this map guarantees the unique fixed point.
I can ask a question.
Mhm.
The policy function, is it the probability distribution? Is it the same?
Usually, policy function is taken by using the certain probability distribution that we need to just choose which types of the distribution we want to use. But policy function just need to be the function that just fulfills all these conditions over here. So it does not need to taken as a probability distribution, for example. As long as it just satisfied all like the argument here for using the contraction mapping, so then it's fine. So that there's also could be a possible like the variation. So this is not the mathematics. So that's the part. So that I cannot really mathematically rigorously define what this should be. So that's why I just say I didn't actually tell you any like regularity of this function, like contingent function, smooth function, all those kind of things. I never actually said.
Yeah, I just want to confirm, is it the
Mhm.
same notation? Because you're both using P for the probability distribution and
Let
also
me see.
policy.
So this P notation
Yeah.
uses this one. So this like a capital P represent the set of the policies in my note. So that
Mm.
there is this notation here.
Okay.
Yeah. Thanks for it. Yeah. Sorry for the confusion.
Mm.
So this P represent the set of the policy functions. So that, and you can check my note from the link I share so that you can also compare by yourself. So given the policy function, then we can associate to this map. Then we know there's a unique fixed point so that we can find the value function. So that the policy determines the unique value function so that we have a map. From the set of the policy functions to the set of the value functions.
Wait, so pi is a policy? Is that the case?
Yeah, types of, yeah. This is a notation of the set of the policy functions.
Oh, so the policy takes like action and states and stuff.
Yep.
Okay.
So the policy determines unique value function. And conversely, if we choose the value function, that is also possible to construct the policy function uniquely by using the property distribution. But it also depends on like context. But what I want to point it out is that this part is not a big deal. So given a value function, then it is possible to also construct a policy. And this part is actually the real issue. So that given the policy, it is possible to construct a value function.
Mm.
And we just want to make the composition mathematically like thinking, so that we just want to make the composition to be the identity for sure. And what we do here is that, so in this procedure, we need to use the Bellman operator from B to V in order to drive the fixed point. This is the whole procedure. This is okay? Yeah, I use this notation here. So this P represents the space of the policies. This V represents space of the value functions. And now we have a unique fixed point by using this.
Mm.
So far so good.
Yeah.
So in fact, this fixed point has actually the meaning. So the machine learning engineers are just taken from the known like the theory of the Nash equilibrium of the game theory. So this is the real the object that was already considered over here, and just the machine learning engineers are just using it. And the purpose of the
Oh, wait,
reinforcement.
I want to ask, the way you construct a new pi from U, which you wrote it like PU, it's kind of like related to the probability distribution.
Right. It is related. So you can just naively, I'm not saying rigorously, assume is that the policy is usually defined in terms of certain probability distribution. So eventually we actually use as a distribution, and usually it uses a Markov chain. So the given data, so actually this matters, and this actually relates to the differential geometry part. So you can just assume that the probability already actually plays a role here in this construction. So the statistical model should be assumed or defined in order to select this part.
So I
So
should assume the probability is fixed during the whole process.
in my understanding, so the heuristically speaking, this is already assumed in the model, like the definition. But this is not the mathematically correct in a sense that actually this should be updated as well. So I do not know some of so there's a base rule. So that actually it's possible to update this part as well. But depending on like the computation, like the efficiency, I do not know which one would be better depending on the context. But usually the model is already assumed in my understanding.
Okay.
But it is possible to update by using the base rule, as far as I understood.
Yeah.
But for their purpose is not to describe everything mathematically rigorously. It's just to make the just better like the performance. Simply that's it. So as long as they can just fulfill that condition, that they actually doesn't really care. But we care. So what I wanna say is that I feel a lot of the uncomfortable like the feeling when I just describe this node, but this is my best. So for the rigorous, but I cannot claim further than this node currently. So the purpose, in my understanding, of the reinforcement learning is essentially just this part. So that given the set of the policies, it drives the certain value function, and we just want to go back. And in order to do it, we need to define the contraction mapping that we call by the Bellman operator. So this procedure is the core of the reinforcement learning. And one of the method is the CNN, or the convolution neural network. So convolution neural network is to just construct this Bellman operator. Then the whole like the algorithm is just running this repeatedly. Simply that's it.
Mm.
So this is just a Stone bias theorem. So the R1 already heard of it. So given a complex set and the continuous function, then we know that there is a polynomial that sum should be approximated nicely. And I think this is reasonable. That's intuitively very clear for mathematicians, right? So given continuous function defined in a complex set, then we are able to find the polynomial depending on the epsilon to make this sum norm conditions should be fulfilled. So this is very intuitively clear, right? And the machine learning, as we already somehow saw, I assume, so because polynomial could be also difficult to use for in practice, so usually one use some activation function. So this is just one kind of the activation function. There are also other kinds. So it depends on the context, which kinds of the activation function is good to use. And ReLU is one of the possible like the kind of the function that one can use, right? And also some other types of function and decomposition could be replaced in this theorem. So it is clear that the polynomial is not really necessary to approximate the sum norm, right? So that one can also use different types of the function, and there are like the types of the certain activation function and also other types of function, whatever that are. So that one can also have certain like the freedom to define those to just approximate the target function, as long as the target function was continuous. But this is some reasonable like the assumption. So the reality is to define the Bellman operator in terms of the matrices, because the computer, like the computing is just for the matrix operations, essentially. So if we go back to this description of the constructed map here, I'm just referring this description here. So if you just compare this description, then you can just simply find. Then as a like a metric, like the notation, we can see viewer function plus gamma some scalar times some probability times just a vector. So and from the as long as if we assume this is the fixed point, then we guarantee this condition. So this part, in general, this is not guaranteed for sure, but if we assume it is a fixed point, then we can simply say, then, well, B should be equal to this guy. So that we just get a very simplified matrix equation. then what you can now recognize is that it is now possible to make the approximation with certain error. So already the reward should be already given in the algorithm, and the P is already prescribed. So by repeatedly apply this part, so that we can update the V, so that we put the input V, output V should be also determined. So the reality is just apply just a matrix multiplication several times, assuming that if we just repeatedly apply this matrix, then it converges to the fixed point. That's the just assumption, but mathematically this is not guaranteed. So heuristically speaking, one just needs to stop in there at a decent time. But the ideal situation is V is equal to this guy, but in fact this is not the case. Is that okay? So this is the heuristical part.
So to begin with, P is supposed to be a matrix because previously I didn't know how to think about P.
So the I understand your question. In fact, this is quite decent. Let me try to explain this part as just a different in the independent discussion, because actually this actually really matters. So that for a moment, let's just assume the probability distribution just correspond to the certain just square matrix for a moment. And then once we just assume this part and this part, then we can just get this like the matrix equation, so that we can just update this V just as long as we have the computation power of the matrix operation. So that what we know is that the theoretical part is that, so given the policy, it determines a value, and we can just run the Bellman operator. It just represents this part. And once we have the value function, it determines the policy, and we will just repeat. And on one hand, we just assume all those functions are continuous functions. This is still the ideal situation. So that we want to approximate by using the Storm-Weierstrass theorem to approximate those continuous functions that we'd like to approximate by using either the ReLU function or the other functions. So that still this is the ideal situation, and the code is also doing, I mean the formula is just do the approximation by in terms of the ReLU function and all those kind of things. So in order to just get this like the ideal situation closely.
So in each part, when you say a fixed point, like from U0 to get U1, it's kind of a quote unquote fixed point because it's approximate.
Yeah, everything is just in fact the approximation, and there should be the certain error. So the error like the control would be matter.
I see. Because I was thinking if it were the fixed point, if you were to do it again, wasn't you supposed to get back the same thing? But
Yep.
then I realized maybe it's because it's not.
So the iteration takes cost very expensively. And this is the major part why you want to use is the GPU.
Before we go into that, I want to ask about the comparison with the algorithm that you're talking about right now, and also when I hear machine learning, I immediately think about the gradient descent, and now we're using another method, which is a just different direction of calculus, seem to be. Yeah, that's very interesting.
Yeah, so in my understanding, the gradient this is just nothing but so given the model, so we know that we can use the chain rule to just update the back propagation is just nothing but the update from the just the output like the vectors as just the input, and just use either the inverse function theorem, the chain rule to just update from one to the other. Simply that's it. It's just a reality, it's just nothing but the matrix operation. And eventually just Cn just means the matrix operation as well. And in my understanding, everything's just nothing but the way to define the matrix operation reasonably. And still, this is nothing but the heuristics. This is not mathematics. So that mathematics is just to get some reasonable interpretation, but the reality is not exactly using the object that we should use because we do not know how to use it. So this is not exactly mathematics, but so we have some like the uncomfortable like the feeling for that, but it's sort of okay. I don't know how to say. So what I want to point it out is that at least the mathematical part of this equation that people call by the Bellman operator is the reality is this is so-called so this is the part that I want to discuss if necessary for the individual like the just independent like the conversation is this is the matrix equation as we confirm is coming from the discretization of the so-called Hamilton-Jacobi-Bellman equation. You can just search it. And instead of talking about the rigorous definition, but we can discuss during this study if some of us are interested in. But what I want to point it out is that this is equivalent to the so-called Fokker-Planck equation. I am not sure that some of you already heard of it, but what I want to point out is that this is just nothing but a certain type of the nonlinear heat equation. So this is a sort of the heat equation, but there's some like nonlinear additional term. Simply that's it.
I think I'm
So
reading from
what I
DQN.
want to tell you is that you pointed out that how to think about this part. How to think about this part. This is all related to this one. So if you now just go back to this like the matrix equation, so the river we will just simply define. So river just is the nothing but the interpretation that so the given the state, and in the case of the Mario game, state just represent the current like the collection of the pixels. Simply that's it. And it depends on the situation. And in the case of the goal, it's like just a current situation of the goal. That represents the state. And we will just define the function that reflects the meaning of the river nicely. Simply that's it. So the river we will simply just define in the depending on the context, but this should be related to the like the for example the space of the state. So we'd like to define the probability distribution to reflect the situation, the space of the state. And in the case of Mario game or the game Go, so it seems like so we want to make some like so there's a situation and we want to define which types of probability distribution makes sense to reflect the space of the state. So the geometry plays a role in a sense that so this is certainly topological space, first of all. And if we strongly assume the space of the states are the smooth manifold, let me just simply say, so suppose we assume it is a Riemannian manifold, for example, then it defines the Laplacian. It associates to the heat equation. So if we assume the data space of the pixels, for example, sit inside of the sphere or sit inside the hyperbolic space, so the corresponding Laplacian should be different compared to the Euclidean Laplacian, for example. And what we know is that if we just assume the set and the space of the state is, for example, just a reader, for example, then by solving the heat equation, we know that the heat equation, the fundamental solution is actually probability distribution. So that you can just think, so given the space of the state, that determines the Laplacian. Then if we solve the heat equation, that fundamental solution, in fact, is nothing but correspond to the probability distribution that we need to get to represent the reflection, a structure of the space of the state. And then what we can do is that we can discretize the given space. Then there is a notion of either the graph Laplacian and the way to discretize the Laplacian that converges to the target Laplacian on the given space. And if we just also discretize the probability distribution or the solution or the fundamental solution of the heat equation, that is the reality, what we really need to use this probability distribution. So that if we play the Mario game, then what we need to think is that this is the space of the state. So this is sort of the geometric space, so that the way to define the probability distribution matters. So in that sense, so for example, if the Mario need to jump for the challenging height, then one need to reflect such like the geometric structure for the probability distribution there. So the geometric structure plays a role. That's what I want to point it out. And one of the things that I feel very uncomfortable as a differential geometer is that so the most of the I think 90% in my evaluation actually just uses just a Euclidean structure for our calculations. This is very far from the necessary structures that they need to consider. And we can take the benefit by simply just changing the Euclidean structure 2D, just the hyperbolic or the spherical, as I already pointed out last time, at least the necessary like the structure of the space of the state, for example. So the differential geometry can play a role to improve the performance of the given like algorithm, for example, and one can definitely consider to write some paper depending on the context. And another part I also want to point it out. So let me now just go back to the website. So first, let me just summarize. The Super Mario game is run based on the DQN first, and I explain what is the DeepQ network. So this is just a run from the reinforcement learning based on the policy and the target or the value function. And if you want to just go deep inside as just for the programming language, then you can find this tutorial. So for the reinforcement learning, now I wanted to show you. So instead of using the Mario game, this is different types of the game from the same library that one can also consider. But I feel like Super Mario is much fun than this weird one. But anyhow, so also there's a packages that one need to install, and I use the Super Mario B not. And the space of the state represent the collection of pixels, so that one need to use the memory to just improve the current like the performance, so that the memory plays a role in the like the code. And now you can I hope now it seems like a reasonable, so that there is the policy function here, so that it takes state and action, and then it takes some maximize like the action to take this guy, for example. So and now I wanted to say that this expression is exactly what I explained in some sense. So there's a reward and there's some parameter, and this parameter is to just guarantee to get the fixed point. So you know what I mean. But for me, it's very hard to explain to engineers why one need to consider this in the like a mathematical like a term. But now we understand why this is necessary, and all others are also related to just make the error control, and all those is actually sort of the heuristics. And if I just go further, so for example, so what I pointed out in my note is that so the CNN convolution neural network is just nothing to just get fulfill this condition. I mean, the purpose of the reinforcement learning. CNN is not necessary condition, but CNN is a very classical and a good like the one of the possible method that we can try to look at more details. And for example, so if we want to take the benefit from just a mathematical part apart, also the algebra can play a role. So I just search like some abstract algebra can play a role. For example, if let me just copy each of them so that if you are interested, you can also take a look. So instead of just using the known theory, one can use the group theory to improve the CNN. That's also possible. Just some, and in my understanding, just some engineer group just uses a certain like the mathematical like the description of the given like the CNN, and also this is just a collab. Let me also share what I found. This is also what I want. Also, there's a way to define the CNN and the convolution neural network in terms of the all algebraic data. So the algebra also can play a role to improve the algorithm of the CNN. That's also possible. And I think I also found, yeah, this one. So that as I pointed out, the space of the state can be regarded as a manifold. In that case, such a like the weight for the Laplacian should be considered. So that in such a case, such a like a structure is also studied very actively. And let me also show you. So such a like the structure are time to time considered, but at least in South Korea, so this is not very active because the engineers are also have some obstruction to understand the basic Riemannian geometry language in minors. But it seems like the China seems totally different. So there are lots of the good engineers understand this type of languages. Let me just copy all of them so that if some of you are interested in it, you can take a look and present. And we can also try to define some project at least just for fun. So that also people try to use the manifold structure to improve the known algorithm, like the algorithm and getting the better performance. So yeah, so in that part, yeah, we can take certain benefit for using the language that we are already familiar with. Right now you can see. So we have for us, we do not to use this like the description. We are all know like the what's the manifold is, for example, right? So yeah, and the T equation matters as I pointed out. But for us, we all know what these are. Yeah, this is what I prepare. So yeah, let me know if you have any questions. So what I will do is that I will also look at the lead code together, but at the same time, I wanna just complete the like the Mario game by using my own algorithm. But in my current like the performance, I cannot even like the go further after 10 seconds. So that I do not know how to make the better like the performance. It's not the mathematical part even. So that I also need to use the hyperparameters to get the try to achieve the better performance first. But it's possible to define sort of the state space, I mean the Mario state space as a certain manifold and try to update the hyperparameters or the like the construction I share by using the manifold structure. And in that sense, one can also consider to do some research to write some interesting paper. But and if some of you are interested, we can definitely talk about it later on. Yeah, so if there's no like the questions, then yeah, I can just ask Wenchuan to share.
Yeah, so I did check papers that he mentioned last time, but I haven't come up with an understanding of things. So I would not talk about that. As for today, maybe I could talk about pretty briefly is what I found online, which is previously there was some sort of generating a photo, generating a video from a photo kind of thing. And currently, if you just try those website, you realize that they're actually not doing very well. So like I try something like the Pika Lab. Um, which is something you could just have a photo and then it would generate a video for you. And but I think the quality is not very good. Um, let me see my library. So I did generate some of the things. This one is like I photoshopped myself like four of me, eight, no, five of me, and then they can generate a video which is only 3 seconds long, and as you can see that the face is very distorted. Yeah. So I would say currently there are things online where you could use, but they're not they're actually not doing that good as you might think. And so here is another one, which is they're called live portrait, and I think they're part of the clean, so something like this one. But this is a Chinese version of the AI. I think they generate the video pretty good, but I can't really use it because you need a phone number in China to be able to use it. But this live portrait is sort of a, I believe it's part of the the clean group, and they did this and made it a open source uh, program where you could just use you can follow all these instructions to download it, and then it's supposed to work, but it does not work very well with the Mac because currently I am using Mac. Um, as for the programming part, it uh the codes are included in here, and then mainly there are things that is I'm not sure which one. Yeah, so things like this that I need to make changes Oh no, I think it's here. Uh, Mainly it's like whether you're using CPU or using CUDA or using MPS. Um, yeah, I did not do the change myself because I don't understand the code that well. I was just using Claude to change this, uh, and also ChatGPT sometimes. Um, yeah. So after making all those changes, oh, maybe this one has what it looks like before the changes. So I just said this was added. Maybe. Yeah. Yeah, maybe I don't have how it looks like before I changed it. Yeah, but mainly the part that I changed was just involving the support for MPS. And after that, it just works. So and it works pretty well in the sense that I can just make videos like this. Maybe I just show you this one. And there was a video of me, and then try to make a creepy thing happen.
So you basically use the already like the trained like the model and just
Right,
the different like the input like the photos and still it works very well.
right. So a big difference with what I did and what Gonghi did was that I did not try to train any model. Mostly, I just downloaded the pre-trained weight, which is available in their GitHub. Um, So what Gyeonghee did was also very inspiring, and I sort of came to realize that maybe I could try to train model myself instead of just try to use them. Yeah,
Yeah, but it seems very interesting. I also wanna take a look. It seems very like the performing very well. Yeah. Any other further comments or questions? Yeah. If not, then let me just start the record for this study.